I'll just start with a brief introduction to AI Camp. AI Camp is one organization which is uh, spread across around 12 countries, and we have 80,000 developers who have joined our organization. And our mission is to bring AI to all developers. So this is one such webinar where we are going to go through the concepts behind a few machine learning algorithms and just work on a few examples with data sets and understand how we can use it in our day-to-day problems. So today we are starting our algorithm. Today we are starting our code journey with an algorithm called KNN. So um, you all must have heard about KNN. Uh, has any one of you worked on it? Any KNN kind of problems or used KNN to solve any machine learning issues? I assume you must be. So today we'll just start with this KNN is actually K nearest neighbor algorithm. This is a supervised algorithm which is used to solve both classification and so it's used to solve both classification and regression problem. So just imagine that we have different data which can be classified into different groups. For example, when a person buys a set of items from a grocery shop, so we can classify those. We can divide those items into groups like grocery or probably cleaning, household stuff, or personal beauty products. So these are the kind of groups that we can make out of data. Uh, so this particular algorithm is mostly, this algorithm is used here. In these cases, suppose in case of market basket analysis or things like that, to actually divide a set of data into different clusters. The main thing about this is that we already have labels for these data. So here we already, if the data is about a list of grocery shopping, then we have the list of all the grocery items with their label, if this is a food item or this is a beauty item, so things like that. And so basically we know we have labeled data, and whenever we come across a new data point, the distance between that data point is calculated with all other training data points, and we decide so and then depending on the depending upon the closeness or the distance, whichever data point has uh, whichever other cluster that the data point is close to, we group that into that particular cluster. The role of K here is that we decide beforehand that what are the nearest neighbors that would be found out. For example, if we have a new data point, a new particular item, which in case of data, we will calculate the distance of that data point with the other data points which already exist. For example, if we have a shampoo, it would probably, suppose we are buying a shampoo and we already have the categories of cleaning data food and beauty products. So probably we will calculate the distance between the existing data points. So we can imagine that the distance between shampoo and the beauty products is suppose zero point 0.1, and the distance between shampoo and the cleaning products is 0.15, and the distance between shampoo and food is maybe 2.5. So we have considered the k of 3. So we are going to find out the 3 nearest neighbor of this data point. Out of this, we will find out which has the minimum distance, and then we will take take that, and we will find out the we will we will actually conduct a vote. So in this case, all the 3 data points are actually different, but in reality what would happen is that the data points would there would be a frequency of the data point. Suppose 2 out of the 3 would be belonging to one particular class, and then we would consider the new data point to be of the same class. So this is how we use KNN for classification. So this is like a very lazy algorithm. We really need for each new data point, we need to find out the distance between that data point and all other uh, existing data points. So this really the speed and the efficiency of this algorithm changes with changes with the number of data, with the number of data points. So the larger the number of data points, the longer the classification algorithm would take. So this is a kind of a deficiency for this, but and it has to be really the more the dimensions of the data, the difficult it is to imagine how to build this KNN algorithm. But the good part is that it is easy to implement. So it can be done as the first part of the modeling process. When we have a clear data, for example, the data has been cleaned after a few uh, after a few set of set of operations. We have data which has been from which we have reduced dimensions. That kind of data can be used here, and whenever there is any new data, that can be easily incorporated into it. So we have the best part is that we just need 2 things here: the parameter k, like how many nearest neighbors we're going to find out to understand the actual cluster where this belongs. And another point is the distance. Mostly we use the Euclidean distance to find out the distance between the new data point and the existing training data points. Uh, but for different kind of purposes, there are different different ways of calculating the distance. But for today's uh, today's webinar, we would be using the Euclidean distance only. So go let's go to find out the data in the code. So here, like I told you, we would be needing to download the data. So please look at this link. I'll just send this link across to you, and you can download it. This is the actual data set which we are using. I'm sure many of you have already used this data set. This is kind of a standard data set that we are using. And this is a very basic code that we have used. You could probably download this or clone this, or if you want, you could go one by one. What would you prefer? Would you like to write code one by one as we discuss, or clone it? Okay, I'll just send it to you. Just look at this. I am sure you all have your Python editors ready. If not, I will, let's take 3, 4, 5 minutes to just get all our Python IDEs ready so that we can just start with this. Anyone has any questions so far? I'm able to access it. How is it giving you 400? Just let me see what's the problem. Yeah, I'm just checking why this is not. I was able to access it, but 1 minute. I have already. I can do one thing in the meantime. I can copy this code and send it to you, and I'll just see why it's not working. Because it should, it was public. I don't know. It's working now. It's good. Okay, if you can just look at what you already have. I will just check. I will just upload one code and see if it's working or not. Anyway, I can do that later. It's okay. We'll just, has everyone been able to download the data set? Okay. So we can just start looking at the code and we can execute it in our systems one by one. So the first thing that we really need to read this data is to import um, the uh, correct packages. So we'll start with, so we need NumPy for storing the results and dividing the test and train data. And we need matplotlib to visualize it, and pandas. If you see, you could read, you could just execute this command to read the data set uh, just examine the data set. So we can see that this has 5 columns uh, uh, for this data set, which is actually the flower. These are the different measurements of the flower which we are using. After you're having problem cloning it, if you could, Cardidiad is having a problem. If you could just try it once again now, I think probably it could, if you could wait for 2 minutes and then try it. What is the error that you're facing? Valid argument. Has anyone else faced the problem in cloning it? Or, all right. So you could just probably copy the paste of copy and paste these codes in your own on your own IDE to just check how it works. So like for every machine learning problem, we have to be very cautious about finding out the dependent and the independent variable. So that's the next step where we are setting up the dependent and the independent variable. The You can see class is our dependent variable, and once we have done that, that is just it's breaking it into x and y, and then we would need scikit-learn model selection to divide it into train and test. So, yeah, so here we have set up the test size to be 0.20. Uh, you can change this test size as per your own estimate. Many in normal scenarios, 30/70 is a good ratio. But here we have just, for this data, we are using 0.20. So this is the SK. So the first step is to read the data set. Second is to find out independent and dependent. And the third is divide it into training and test data. So in machine learning, the training data would actually be the data which would be analyzed to find out the patterns. So the training data would be analyzed, the KNN calculation would be done on that training data. And then once that calculations are done, we would use the test data and we would use the test data to predict the values, and we will see how well the model predicts uh, the class for our test data. So after training and test split, we have another special step of using a standard scaler. So that is to normalize the data. So by normalize the data is that we are the k-neighbors classifier in sklearn would take a standardized data which has a mean of 1 and variance 0. So this standard scalar would sklearn gives us scikit-learn gives us a facility of using standard scalar, uh, which would actually transform the data for us. We don't need to worry about anything. This the so we need to use the standard scalar to get a normalized data. And after that, from scikit-learn, we will use the k-neighbors classifier. Here, if you see, we have mentioned the number of neighbors as 5, and then the classifier.fit is actually so classifier.fit is using X train and Y train. So this data contains the value of the dependent variable and the independent variable. Uh, the classifier from scikit-learn actually analyzes this data to find out the patterns. And this data, the classifier.fit classifier is actually what we are going to use later to predict our data for our uh, independent variable. So you can see this. Have you been able to run the code so far? I assume. Okay, Kadi. Yeah, so this data is Kadidi had asked what is the benefit of using a scalar. So this data that we are using is actually random, and the variance and mean is actually quite diverse. But we need to use a normal distribution for our k neighbors. K neighbors. Algorithm that is implemented by scikit-learn. So that's why we use standard scalar, which would convert our data into normal distribution. So the standard scalar will change the mean will bring our data to a format where the mean is 0 and the standard deviation is 1. I think I probably mixed mixed it up, but the mean would be 0 and the standard deviation would be 1. So this would transform the data, and we can use the output directly into scikit-learn k neighbors. There's another question of why do we choose k as 5? It's just a random number. You remember that we need to have a vote for the new data point. We need to vote which class it belongs to. So it makes sense to choose an odd number where it is easy to vote. If we suppose, and if we use 3 or and the number should be medium size. I mean, if we use a very small number, then it's not very easy to understand which particular class has the most number of frequency or has the most proximity to the new data point. So that's why we always choose an odd number, and we have chosen 5 because then by choosing 5 there would be when we have to vote for the best class, we would have a better number to choose for. Suppose if we choose something like 3, then each class may have a very it will not be very clear to pick which particular class the new data point belongs to. So this is a rule of thumb, but mostly the a kind of unwritten rule is that it should be an odd number, and it should be uh, at least at least 5 or more than that. So in this data we can have 5. If we choose, you can for your own benefit, you could use. Yeah, I am answering the same question here. So for your, if you want to test, you can test it with 3 also. But this is just 3 would be very difficult. It would take a lot of time for each cluster to find out the nearest neighbor and then vote the best possible class for that number with the maximum frequency. So does this answer your question? Okay, all right. And yes, for our benefit, we can even try with 7. I can try with 7 and see how it goes. And run it. So once we have built the classifier, we have done the first step of fitting the data. After that, we can now use this classifier to predict the data. So if you see, our next step is now to use a predicted variable of y using the test data. So if you check the x, I mean, whenever you divide data into test and train, the test data will not have the actual values of the dependent variable. So we are just trying to predict it uh, using our classifier. So we can check all these. These are the different classes that they have predicted. And right now, it doesn't make a lot of sense for us because we don't know what the classifier is, or I mean, what class of iris it should be, iris virginica or iris versicolor. So um, it's always that we need to. Um, yes, that's that's one uh, that's one issue. So to find out the actual way that our code is working correctly, we need to go to this particular. We need to use a class from sklearn, which is sklearn.metrics, and we will find out the classification report and the confusion matrix. The classification report would be able to tell you exactly what is the precision, what is the recall, what is the F score, and then we can statistically see what is the whether this is a good model or not. So this is very simple method of doing it. You can, if you want to understand KNN very well, we can write a code where we will actually take all the data points and calculate the Euclidean distance, and then just find out the neighbors, poll poll the neighbors to find out the best alternative for the class. But that is obviously a very inefficient way, and it takes a lot of memory and a lot of processing time. So scikit-learn has given us this facility, which is easy to use. So you could, this is just one way of doing things. In real life, KNN can only be used when we have uh, less number of dimensions and relatively less data, or our we can use the KNN as a first step when we are not really when we are just randomly, we have some data and we want to find out what is the normal tendency of that data towards. So I can see there are some more questions. So what what would you like to know about the YPRED output? When we fit the classifier, whatever, so when we fit the classifier, that particular input data set contained all the 5 columns of this data set. So they contained all the petal length, sepal length, and the class. So internally, what internally the classifier has calculated that if petal length is 5 and sepal length is 3.2, for example, and uh, the column 3 value is x. So what are the fields? Let me just check it once again. So petal length, sepal length, there are, suppose there are a set of values, then that particular iris would be iris virginica. And if sepal length is maybe 7 and sepal width is 2, petal length is 6 and petal width is 1, then it would be iris versicolor. So this is what they have found out uh, from from the classifier.fit data. Now, when we are sending this when we are sending this XPRED data set to the classifier.predict, it has uh, all the four columns, that is the sepal length, sepal width, petal length, and petal width, but it does not have the class of that particular iris. So based on these 4 columns and based on the patterns that have been found out from the classifier.fit function, this program actually, a scikit-learn classifier will predict the most likely class. So it will not be, I mean, then so this is the most likely class. And then when we run the metrics, we find out whether this class that our classifier has predicted is actually correct or not. Does this make sense to you? Yes, it is predicting the points. Yes. So we always have to set up one, yeah, we have to identify one particular parameter that we are going to predict, and that is actually the dependent variable. And then there are these 4 the other columns which are actually determining this particular parameter are the independent variables. So the value of our class, the value of the class of this flower depends on the petal length, sepal length. So these are the parameters actually which are governing the class of the flower. And this is an easy example, but the reason behind explaining this algorithm is that we have applied this to an iris flower dataset. We can apply it to any other dataset. The prediction precision uh, will not be great. So it will, I mean, the prediction will not be correct. We cannot really. So Mark has asked a question that what happens if you don't use a scalar? So that's my answer, that sklearn is expecting data which is normalized. If we use a different kind of distribution, it would be very difficult it would be mathematically incorrect for the classifier to calculate the clusters out of that data. And so that's why the predictions which would be done after that classifier, like if we use the data without any scalar and then we send it to the classifier, we run a classifier.fit and then we predict data. So that prediction will not be correct because then the calculations that have been done internally have not been calculated properly. So the clusters may not be right, or it might, yeah, it will give incorrect result. Is that, does that satisfy you? You could even try once. You can do one thing that you can skip that step and see what is the prediction that's coming out. It will not be the same as this one. So shall we proceed, or is there anything else that needs any explanation? Yeah, I think that is all right, because there is a lot of probability that is involved here, and Nathan has got different results from what I got, so that is not really that's not something that we should be very concerned about, because more or less we are concerned about the prediction which which should happen. Yeah, you can, for anonymous attendee, you can check, like when I'm printing the Y spread, you can also print the X spread, and then all the columns of, I mean, the rows should match for each row in X spread, for each set of columns, for the columns which consist of the flower details. The Y spread value would be the class. So if you see, uh, this is what, sorry, this is the, uh, this is our format. And so out of these, so X spread has these uh, four columns. So you can you can match this with Y, and that way you will be able to find out. These are the set of characteristics that determine the class of the flower. Does that answer your question? Okay, so Mark has a question that what happens if rows are randomized? I think scikit-learn should be able to uh, we should be able to process it, and we are using a scalar anyway. But I think we should, yeah, you could try this and see. But internally, when we are running the scalar, it would again be ordered. But I think the random data can also be entered into this. There is no requirement that it should always be ordered data, but it's just that for random data it would take a little longer. But yeah, but we can definitely run a random data here. And anyway, we are running scalar again on top of it. So it's just our responsibility to clean the data before we run a model on it. But theoretically, like, it's not impossible to run this with random data. Do you think that's all right? So should we, I think the next, if we do not have any more questions or any more ideas of working on this, we can move to next. So what would you suggest? Should we take a small break before moving on to next, or this is fine? We can go ahead. And Nathan, it's just that we are using a lot of random samples from the data sets. So that's why we would not get the same set of precision and the confusion matrix, but I think the prediction should be still correct. Precision, yeah. Okay, so now after taking a look into the KNN, we can move on to k-means. K-means is a little uh, complex algorithm than KNN, because in KNN, if you remember, we had data with their labels. Like we knew we had this data, and we we could classify the petals and the sepals and we could find out the class from them. But here we are not going to have any labels to any data. So this is an unsupervised data, which is called k-means clustering algorithm. And so this is again an algorithm where you have a set of n objects, and then you just break it and you move it into k clusters. So in KNN, we were using the letter K to identify the nearest neighbors and to identify the number of nearest neighbors we should check and then find out the best match. But here actually we are actually by K we mean the number of clusters here. So it is like you have a set of observations and uh, you would like to divide it into some number of clusters. You say here also sometimes for our benefit we use a random odd number again for k-means clustering, and so we start we we tell the algorithm that okay, these are I want my data to be divided into 5 different clusters. So the data would actually randomly take 5 different means in the data, and then find out all the data points which are near to that mean, which have the least distance from that particular point, and then that would be considered the cluster. So this is like a repetitive task. So the first pass, when we tell them when we are building the clusters, that cluster is always inaccurate. It's just a random thing. Then the next time when we start, we do not the k-means, the means are not random anymore. So first time we have taken a random mean, and then we have calculated the nearest points, and then we have considered them the cluster. Second time we take this cluster, find out the mean, then that becomes our new k-mean. And slowly we keep on repeating this approach again and again. By the time we have a set of cluster where nothing changes, like where after that, after a certain point of time, the number of data points in one cluster becomes stable, and this is how it keeps on going on, and one by one. So I know it is a little difficult to understand. If you can just read this, and then we will take it, we will take an example where we will first calculate k means through a normal uh, loop and normal traditional method, and then we will use scikit-learn, so that will make it clear for us. So k-means clustering is used in building recommendation systems. So for a person who's watching some random programs, they can, excuse me, excuse me. So they can, uh, so that data can be formally clustered into the top categories, maybe top 5 categories that they want to watch. So things like that, there we use k-means clustering. So have you, I mean, did you go through this? Should I go to the code directly? For this code, we do not have, since we wanted to explain everything to be done through code and then through scikit-learn, so we have not taken any data set here. It's just some random data. So please let me know if you are able to open this link. Okay, so I can start. Uh, I can start my explanation with the first part. If you see, we have just randomly taken two X and Y uh, columns in one data frame. So that is our that is our input. So our first step is to take some random centroids, and here we have taken k equal to 3. We have just randomly taken some some centroids. By centroids we mean the k means actually. So centroids are actually the set of means. We have randomly taken means for these number, and these are going to be our cluster points for right now. Can you see how the plot looks? I'll open my code and once run it too once. Are you able to intuitively understand what this is doing? See, the first step when we ran, we can see that, okay, so the centroids actually, these are the k-means. Like I told you, that we will, in the beginning of the data, we will just define random random means. So these centroids are actually those means. I have just used the word centroids here, but because that's the statistical language. So what we are doing here is that just we are setting up uh, a dictionary with a random number here, and that is these are actually uh, the means within this data space. So if you can see, we right now we have 3 ks3. We have these 3 dots. One is blue, one is green, one is red. So these are the 3 clusters that we have decided that our code should have. Our data should have. Sorry. Now this is completely random. There is no relation to the data that we have. So that is why you can see that the first pass, when we just did the k-mean, that is completely wrong. There is no meaning of doing this. No meaning. This has no relation to the data. This is just something that we have done randomly. Now the next stage would be the assignment stage. In assignment stage, what we are doing is that we are actually finding out the distance between these dots, this green dot, and the different data points. So what would happen after our second pass is that this green dot would probably, we need to change the value of the green dot such that it is nearer to these data points. So here we are not, we have the data which is static. We are just going through entire data again and again to find out the right value of our clusters, because we don't know anything like this is completely unlabeled data. So that's why we have to go through this complex task. So now when they have, so now what we have done is that we have found out the points which are nearest to these dots so these are the points which are nearest to green dots, so this is considered the cluster green. Then these are the points which are closer to blue, so this is considered cluster blue. And then this is closer to cluster red, so this is considered cluster red. So now first we found out random means. Then the second, we found out the clusters which are the data points which are closest to them. So even if these clusters are not correct, we at least know for this hypothetical cluster what are the data points uh, which would really be a part of that cluster. So this is also a preliminary stage. Now we go to the next stage. So if you look at the code, I think I can explain the code, but you can understand it that what we are doing is actually that we are going through the entire data, calculating the distance here. So this distance is actually Euclidean distance. There are many other ways of doing this. There are also, uh, I believe, there are Python constructs which can help us, but this is just for our understanding that we have kept this. Okay, so moving on to the next. Now we found out, we started with the random mean, we found out the data points. Now we know that that is not the right mean. So now we have to update our values. So let's run this and see how it goes. I don't know if I typed this in. I'll check that code later, but you can just, I'll update that code and send it to you. I think I mistyped something. But if we, I mean, by when we keep on repeating the assignment stage, slowly, slowly these clusters would move. I mean, the cluster points would slowly move closer to the data points. And then there would be one stage where we do not get any changes in the cluster. So if you see now our cluster points have moved up. It's just within the data. In real life, we would not need to do so many loops and understand how the cluster is moving, how the center of the cluster is moving. This is actually the centroid or the mean which has moved. So we started from a random value, kept on iterating until the value of the mean did not have any significant change. Scikit-learn has a very easy way of giving us of getting this done, and so we can directly use k-means. So here there is no testing or training data because for us the entire data is test data. We don't have any data to train our model against. So this is just going to be uh, just one code. So basically we are using the predict function here again, but since we do not have the training and testing data, we are just moving it in, we are just running the entire data set here. So I have to check. This is some incorrect code here. Let me just check something. I'll correct this code and I'll send it across. Um, I'm sorry, this is some mismatch in the print, but I can just, we can just print labels and see labels and centroids, how they have been calculated. Oh. Okay, so the code works for you. That's, I'm a little, yeah, this code worked for me when I tested it earlier, but now I don't know why it's not working. But that I think something, yeah, something, I need to change the editor here probably. So are you able to understand this? I mean, are you able to understand the logic behind k-means where we use it? The main thing that we need to remember is that we, for k-means, we will not have any testing or training data, and we're directly going to use the scikit-learn k-means, and the number of clusters we will define, and it would find out the labels for each data. Do you have any questions? Any questions on this? I think the next topic that we have is ARIMA, which is about time series analysis. So if you have I think we can take a 5 minute break and to come back and refocus, because that is totally different from this classification problems that we have been doing so far. So would you like to take a break, or is there anything that you would like to discuss now? Okay, so I'll pause my presentation for 5 minutes and return. Uh, I'll return with some code discussion for ARIMA. It is a little difficult one. I mean, it is a little complex. So what I would suggest is that probably today we can absorb some of the concepts, and then later on work on it by oneself to analyze the problems. Sure, I'll just do that. Yeah, I'll just, like Mark suggested, I'll share the data for you, and I'm just, it's very small data. So I'm back. I hope you have been able to download everything correctly. Okay. So yeah, we have around 30 minutes to discuss this, but this is a little different from what we have done so far. You all must have heard about time series in your field of work. So so far we have been doing data set which is discrete, which is just uh, uh, stable, stationary, you could say. And now we will work on time series. So time series is a series of observation over a period of time. So the data changes with time, and this is the most common way of doing a common application of data science, because businesses, share prices, wherever you see a time series is what is actually of interest for people. So it is used for forecasting how trends happen, how prices change, or how demand changes with uh, different weather conditions, or in different months, probably the holiday months, how the holiday months add to the consumer behavior. So this is what time series is like. So if you read it, it is the full form is really a mouthful. It's autoregressive integrated moving average. By autoregressive, what we mean is that the so uh, if you can get a stationary snapshot of a time series. Okay, before I go into these things, so is the idea of time series clear to all of you? It's just adding a new dimension of time to our data. Is everyone here uh, to resume our conversation, or should I spend some more time? Okay, so there's no uh, there's no message on the chat window. I assume that everyone is okay with this. So it is like a timeshare time series. So that is okay, Galaxy. Do you have any question? Yes. Okay. Should shall we start? I'll just go over the concept of time series once again. Yes, the time series, like you all know, it is actually analysis of data across a period of time. This is what is of interest to most business people, because they need to see the trends, how data is changing, and how uh, a particular set of data vary over a period of time. So that is a time series. Usually, the time series data ranges over a year, sometimes over a year, sometimes it's over a few months, sometimes it's a weekly data. So it is very difficult to predict the time series data, because all the parameters of this keep changing. So the mean changes, the variance changes. So we cannot really use our models which we have used for uh, normal data frames so far, where we did not have the dimension of time. So, so the that's why statistics has this method of auto-regressive integrated moving average. It sounds very difficult, but it is actually, if it is broken down, it is quite easy to understand. The only thing here is that you uh, we we cannot analyze something that is changing regularly. So what we have to do is actually we have to catch a snapshot of a time series and then analyze its behavior. And we can find out patterns from that snapshot and then use that for predicting values in the, for for the future. So of course the precision and the predictability is a little difficult here, because with time there are a lot of unpredictable factors. So by autoregressive, what they say, what the word autoregressive means is that if we can capture a stationary time snapshot of a time series. By stationary snapshot, we mean a snapshot of data for which the mean doesn't change. And if we can capture it, then the time difference between the the time difference can be used. I mean, that particular data can be actually used as a linear regression model. And one of the parameters in that linear regression model would be the time lag. So that is, um, yes. So in one way, you can say that it's a linear regression based on a past value of a uh, particular variable. So if we can capture a snapshot, then what for example about sales. So this auto-regressive model suggests that if we can capture the data in the month of July, then this data can be used as a linear regression model for the future. So this is the autoregressive integrated. Uh, Integrated means that we are actually we, instead of using the changing actual time series data, we are capturing the difference between one particular between different time intervals of a time series and using that as our data. So that's why it's integrated. And moving average is that the the average is changing over a period of time. So even though this is here, we wouldn't need a lot of statistics to understand each small part of uh, of this. But for us, what is more important is that we can understand the practical implementation of this, and then later on we can go in depth. There are lots of basic building blocks that we need to understand. So before we understand this, so Um, so these are if you see, if you look at any literature related to ARIMA, there is a Box-Jenkins method that is used to calculate this ARIMA. This is basic. This is a statistical method that was introduced in 1970s. So that is the method that is still being used here. Uh, these variables P, D, Q are actually also quite standard with this model. So by P we mean the number of lag observations. That is the number of time interval observations that we are taking. D is actually the number of times the data has to be differenced. By difference, what we mean is that, like I told you that in time series the mean is changing all the time, but we cannot analyze any data for which the mean is changing. So differencing is actually finding out the difference between finding out the difference between the values of data between different time intervals uh, repetitively until we get a stable mean. So this is like uh, x at t, um, x at t minus x at t minus 1. This is first difference. If we see that even this has mean, this has uh, a changing mean, then we will have to find out x at t minus 1 minus x at t minus 2. So we have to keep on finding differences. Thankfully, we don't have to do this. I mean, we have scikit-learn, so that's taking help. That's helping us. And then Q is the moving window. So I can let me think of uh, an example for Q. So this is actually the order of the moving average that they say. So moving average window is basically the window of in which we are classifying the data. So it's actually moving average is a moving window. Moving average window is actually the time interval within which we are analyzing the we are analyzing the values. So this is also theory. Uh, for building a ARIMA model, we don't have a scikit-learn, but we have stats model. So we are actually going into statistics to use it. So if we have to first, so the steps are similar. It's just that we have to identify the P, D, and Q parameters for a particular time series. And then once we build the ARIMA model, we have to fit it to our existing data. This would again have train and test data. So it would first fit the test data to the ARIMA model, and then we will use that model to predict our the the fitting would be done with the training data, and the predict would actually go and make predictions for the test data. So here we have used an ARIMA model of 510. Uh, So this is the steps of Box-Jenkins methodology. I think if you are interested, you should read this. This this is almost 125-page chapter in a book, and it is not very. I think it would be out of the scope of this discussion. But if you're interested, you can read this Box-Jenkins. Um, so they just talk about the 3 steps here. That first you have to identify the model and parameter, and then iteratively check the model to find out the best possible model. Since we have stats models, we are not concerned about this, but it is always good to know the actual calculation. So now let's go to the code. I have it here. This k means, and this is ARIMA. Okay. So Okay, so we have this is the data set that we are reading. If you so we are reading it, we are reading it as a series, and just plotting it. So this is how it looks. This is the shampoo sale data set that we have. The year is randomly set to 1901. I don't know if they had shampoos then, but yes, Mark, I will be sharing in fact, I can share it right now. I just have to make sure that it's available for everyone. I'll be sharing it with all attendees. No problem about that. And I'll actually share it uh, to the group at Meetup, if that's all right. So this is the first plot of our time series. It shows change in shampoo sales from January 1901 to end of 1903. So if you see, it is increasing, but there is a lot of changes here. It's not easy to analyze this data. So then there is this autocorrelation data to see whether we can use um, this code in our for our analysis. So if you see, we have used pandas library to help us find out the autocorrelation plot. So you can see that it is more uniform than our time series. So autocorrelation actually tells us about the correlation between the value of the same variable over a period of data. So for example, this here we are calculating the correlation between shampoo sales and shampoo sales across different periods of time. So so does the shampoo sale in July 1902 depend on the shampoo sale of July 1901? So that is what we want to see. So actually, if it is like that, then uh, yeah, the autocorrelation plot tells us whether we can go ahead with the ARIMA or not. And since we can see a kind of a trend in this graph, we can say that there is autocorrelation between data points at different times. So it makes sense to go through ARIMA on this kind of data. So then we go to the next stage. We use the ARIMA model, and we are using the parameters 5, 1, and 0. Uh, so this here, the first parameter is actually um, so here, this is where we have explained this, the parameters Q, D, and P. So first is the number of lag observations included in the model. So that is the number of observations we are going to include to find out the pattern. The number of times the raw observations are differenced. So we have only calculated, so our model is 5, 1, and 0. So 5 is actually the number of observations we have included. One is we have just taken one difference and just after taking difference between two intervals, we saw in autocorrelation plot that the plot was smoother, so that the mean did not change in that. So we have just taken one difference, and then the size of moving average is 0. So that means that we don't uh, that means we are taking all the five observations in our account. This is, yeah, 510 is our model here. So let's go back to our code here. Here we have our code. So we built it with 5, 1, and 0. So our model has done the analysis and found out the pattern. Now we will add, we have just added model.fit. After doing the model.fit, we are going to find out the residuals. Residual is actually the error, but we can use this to predict other, data, which we don't have that kind of data, but we can do that later. So this is the result that we are getting from the ARIMA model. Yeah, we will do that. Yes, this is the result that we are getting. These are the residual, these are the errors actually. The error between the expected value and the actual value. And the next step is actually the prediction. So here we are again using train and test and finding out the predicted value. After we first done model.fit, then we are using a method called forecast. So forecast is uh, uh, actually predicting the data for the future. And then we are building a new model here. So we have two models here. One is prediction and the actual one, the test data and the prediction. So we can see the predictions are marked in red. So this is the difference between the test data and the prediction. So is this code running for you? This moving average, if you would like to understand it in terms of normal, in terms of its application, this moving average is used to smoothen the curve and just filter out the high frequency data. Here we do not have a uh, very diverse data, so we have used moving average window as 0. But uh, usually when in real life, the, it would require some functional knowledge and the knowledge of data to understand what should be the correct moving average window size. We can set up the first two parameters easily because, but of course, we need to know the data. We can say that okay, we'll take 5 lag values or 6 lag values, and then we can understand that differences, how many differences we need to take. But the moving average window size would need a little bit of would need little context uh, about the data. The smaller the window size, the more the changes get picked up. I mean, the more the window size in one way is actually affecting the sensitivity of the value. So the smaller the window size, the more sensitive data will get picked up in our analysis. And bigger window size, that means that we are dropping off some data and taking it, we are just the granularity of our data analysis is going less. Mark, how would you mean the direction of change in momentum? In case of time series, how would you think that would be affected? We cannot read. I think in this case it is going to take the past behavior as an indicator of the future behavior. So if the past behavior has ups and downs, then the future behavior would also be predicted to have the ups and downs. So it is not exactly momentum of direction of change, but whatever the the past behavior of a time series uh, can be considered a good predictor of the future. So in very broad way, it could be a momentum of direction of change. But then this for a wider or for a broader set of data sets, it might not be really applicable. So what I would say is that this may not be exactly translated into the behavior, but sometimes for some kind of data, this algorithm would behave as if it is taking the momentum of direction of change into account. But that is not actually guaranteed in all situations. Do you agree with me, or do you, would you need a little more analysis on this? I think the window size is actually it will not give us momentum. It will just decide what kind of data we are taking. So it decides the granularity of the data that we are taking into consideration. For values which are which vary very fast. So the graph is very complex. There are lots of ups and downs. In that case, if we have a larger moving average window, then in that case we are able to group a um, lot of varying data into one block. So that is going to that would a larger window size could reflect the overall direction better in case of uh, uh, a data with a lot of variance. In a stable sort of data where we do not have lots of changes, then we don't need a large moving average. So this is like mm, that if we have a large moving average, what means is that a lot of noise gets reduced. So some of the observations may be valid, but they may not be relevant. So if we take a large moving average, we will be able to reduce the effect of those irrelevant observations in highly variant data. You understand? It is like a granularity kind of a thing. The smaller you go, the more details you are taking from that graph into account. So that means if like here we have used 0, that means each point is getting considered. But in real life data, for example, just imagine sound waves, or when we if we have a graph which is representing sound waves, so just think how many variations it has. If we take 0 as moving average for that kind of data, so that means we are taking into consideration each and every data point, and it is adding to our complexity. And it is just it may give us some result, but it may be there would be a lot of noise in that. So in that kind of thing, we are taking one. You could consider a square that we are building in that is. Probably that by, I think you mean by window size, you mean the number of observations that we are taking into account. So that is not, I mean, the number of observations that we are taking into account is called the lag order. So that is, so the larger the number of lag order, the better the overall trend is. Within that lag order, the minimum unit of our for our observation is the actually window size. So just let me show you. So this within the lag order will determine the trend setting, the trend analysis. So we need to have just the correct lag order so that we can identify the pattern. The differencing actually is our responsibility to bring the data into a stable mean format. And then this size of the moving average window is actually the granularity within the lag order, that how much data we are considering within the lag order. So if suppose we have taken a snapshot out of a time series, that is our lag order. And that so we have a we have the data for 5 years, and we have taken the first year as our basis. So that is our lag order. And maybe just taking, instead of first year, if we take 2 years, that would give us a better output about the trends. So probably that is your point, Nathan. Am I right? No, that moving average is not for that actually. First, it is between that, what is the minimum set of data that we need. For 2 years, we have the lag order, or you're taking a snapshot out of the 2 year, and then you're for 2 years, and then you are analyzing it. So then this entire data of 2 years, you need to identify whether you want to check each point in this data, or you're going to consider a set of points as one entity. So that decide this window, actually we draw a window across a set of points and say that all these points actually map to one data point. So that is the moving average. If we cover it for two, I'll just see. I I believe that, and this may not be exactly the same year, but I'll probably find out and let you know. That is actually calculating the moving average across, and here we are talking about the moving average window. So yeah, so here what we are, in this case, what we are doing is that we are just adding this to remove the short-term variation in our data. So what 250-day moving average is a different model that they have built. Yeah. That they have built using the data, and then they are finding out how the average is changing. Yeah, so now we are out of time. I am we just went through all the concepts. Hopefully you would you would be interested in knowing more and explore more on your own. And if you need any more documents or any help, I can you could reach us at the meetup website. This was more of just going through the basics. I'm sure you can build much more useful items out of this. You can use this for data analysis. You can use this in Kaggle competitions. This is a starting point. Hope you can take this forward. So if are there any more questions that you would like to handle before closing this? I'd consider that a no. So thank you all of you for joining and staying in the meeting for so long. Thank you for spending your 2 hours. Hopefully you have learned something, and hopefully you enjoy the rest of the day. Thank you. Bye.